All right, so we're in section, we're doing 7.1 and 7.2 together. All right, let's stop talking, please. So ratios and similarity. First off, let's make sure we understand what we mean when we talk about a ratio. What is a ratio? What do we mean when we're talking about ratios? Any ideas? Compare, it has to do with comparing. Right. So that's how, for every certain amount of one thing, how much of another thing do we have? So it has to do with comparing, and we do it with fractions. So comparing two things using a fraction. And we usually write, so we write A over B, or we can write our ratio this way, or we just say it A to B. So we could say 2 to 3, so we get two cups of flour for every 3 teaspoons of salt or something like that. So that would be a ratio. We usually, not always, use the same units. But like the example I just gave, 3 cups of flour to 2 teaspoons of salt, we don't always use the same units. So we usually use the same units, and we write our fraction in lowest terms. So we reduce our fractions. We can also have an extended ratio. And an extended ratio just means we're comparing 3 or more things. So we write an extended ratio, we could say A to B to C. And the fractions that we would get would be A over B, A over C, and B over C. Same, so these two things mean the same thing. So it's just a relationship for 3 or more things. All right, we good there? Okay. So what we're going to do is use ratios to make proportions. And proportions are just equations between ratios. So what we did on our opener was a proportion. And we decided we solved them by cross multiplying. And some, I know, depending on how you learned to work with proportions before, had students in the past. I had a class a couple of years ago, and they talked about using the fish. And the fish is just a way to help you remember how to cross multiply. I'm always just going to call it cross multiplying, because what I remember the students would get confused about how to do the fish, and then they would have a hard time setting the problems up right. If you remember to cross multiply, you'll be set every time. So just really quickly, if we had something like 3 over 8 equals 5 over x. So something like our opener. We cross multiply, we get 3x equals 40, divide by 3, so x equals 40 thirds. Now I have to be careful in a couple of situations. Sometimes we'll get a proportion like this. And what I suggest that we do, we still cross multiply, but anytime you don't have just a single thing in either the top or the bottom of one of your ratios, I suggest you write a set of parentheses around it. And that will help you remember to multiply correctly. So then when I cross multiply, I get 6 times the parentheses x plus 3 equals 12 times 5 is 60. And then I could distribute here and solve it this way, but this one we can take a nice shortcut. If I just divide everything by 6, I get x plus 3 equals 10, so x equals 7. I'll get the same answer if I distribute here and solve it that way, but this gives us a nice little shortcut. All right, question. All right, sometimes, in this chapter it comes up, sometimes when we solve a proportion, we end up with a quadratic equation. So I want to take a little detour and talk about quadratic equations. So a quadratic equation means that we have something like ax squared plus bx plus c equals 0. So we have an x squared, an x, and a number, and it equals 0. To solve a quadratic equation, we have to factor or the quadratic formula. And just as a reminder, our quadratic formula, x equals, we have a quadratic equation like this, negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we have a quadratic equation, we have to use either factoring or the quadratic formula to solve it. And sometimes that happens when we work on it, when we solve a proportion. So I want to do an example of each one. So let's say we want to solve the proportion x minus 3 over 3 equals 2 over x plus 2. So I'm going to, my hint is to put the parentheses around these. So you remember to multiply correctly. And now we're going to cross multiply. So when I cross multiply, I get x minus 3 times x plus 2 equals 6. Now what do I have to do? What do I have to do with these parentheses? Well, so we do have to FOIL. They're already factored. We need to FOIL to multiply these together. If it helps you, you can write FOIL over here. Remember, FOIL means first, outside, inside, last. So the first two numbers, x squared. The outside 2, 2 times x. The inside 2, negative 3x. And the last 2. Negative 3 times 2 is negative 6. And I add all those together. So x squared, 2x minus 3x is minus x minus 6 equals 6. I want my quadratic equation to look like this. So I subtract 6 from both sides. And I get x squared minus x minus 12 equals 0. I have a quadratic equation there. I either need to factor or use a quadratic formula. Can we factor this? Yes.
Even though it's minus 6, you can still subtract 6 from this.
I subtracted this 6 from both sides. So I subtracted this away to get the 0 there. Can I factor this thing? To factor this, I need to find two numbers that multiply to negative 12 and add to negative 1. Are there two numbers that multiply to 12 and that are one number apart? 3 and 4. All right, guys, the chatter. This is important. If you don't get this, it's not going to turn out well. All right, so we're going to factor this. So we need a 3 and a 4, and I need to multiply to negative 12 and add to negative 1. So it's going to have to be a plus 3 and a minus 4. This tells me that these two numbers are multiplied together to get to be 0. So one of them or the other one has to be 0. X plus 3 equals 0, or x minus 4 equals 0. Subtract 3 from both sides, I get x equals negative 3. 4, add 4 to both sides, x equals 4. So I'll get two answers here that would make this proportion true. So there's our solution by factoring. Mm-hmm.
So how do you determine which number is positive, plus 3 minus 12?
They have to multiply to negative 12 and add together to give me this negative 1. So negative 4 plus 3 is a negative 1. And 3 times negative 4 gives me negative 12. If I would have picked it the other way, it would have turned out to be positive 1 instead of negative 1. All right, questions there? All right, let's look at an example where we have to use a quadratic formula. So we're not going to solve a proportion. I'm just going to give us our equation. So we're going to use a quadratic equation. This number in front of the x squared is a. This number in front of the x is b. And this number in front of that's by itself is c. We're going to plug these into the quadratic formula. So x equals negative b plus or minus the square root of b squared. I'm going to write it all out. Minus 4 times a times c. All divided by 2a. And then I just need to simplify this. So I get x equals 10 plus or minus the square root of negative 10 squared is 100. And I get a 8 times 11, negative 8 times 11 over 4. A 100 minus 88 is 12, yes?
Wait, I'm confused. Do we do the factoring out of the FOIL after we're done using the quadratic formula?
No, so we did the FOIL. You're talking about this one?
Yeah, how do you know which one to do?
Well, the quadratic formula always works. Factoring, if we can factor, it's usually a little easier. We figured out if we could factor just by looking at the numbers and seeing if we could find two numbers that multiply to negative 12 and add to negative 1.
If you factor at each time, though, does that work too?
Well, so not every quadratic equation will factor. So sometimes they won't factor. You won't be able to find those two numbers that work in the parentheses. The quadratic formula will always work. So this one, we couldn't find the two numbers that we multiply together that would work out right to give us all these numbers. We couldn't factor this one. Factoring doesn't work for this one. All right, so now we're to here. We need to simplify. Sometimes we'll get our questions will ask us to write the answer in simple radical form. So we need to simplify this radical. Square root of 12 is the square root of 4 times, or square root of 4 times 3, and square root of 4 is 2, so that's 2 square root 3. So this equals 10 plus or minus 2 square root 3 over 4. And all of these numbers here I can divide by 2. So I get 5 plus or minus square root 3 over 2. So our answers for this one are x equals 5 plus the square root of 3 divided by 2, and x equals 5 minus the square root of 3 divided by 2 are two possible answers. So we use a quadratic formula on this one because it wouldn't factor. And we also used our simplifying radicals that we did a little practice with a couple weeks ago. All right, questions there? Okay. Now let's get into what the real kind of the gist of chapter 7 is. We're going to talk about similar polygons. All right, so first off, let's talk about what we mean by similar. We've talked a lot so far this year about things being congruent. What would we guess we mean when we say things are similar? Same. What do you think, Kay? So we said congruent meant same size and same shape.
They look the same, but they're not.
There's something about them the same, right? Same. Would a triangle be congruent to a square, or not similar to a square? Same shape, right? But different side lengths or different sizes. So that's kind of going to be our everyday definition of similar, is the same shape, but not necessarily the same size. Because could something be similar to itself? Yeah, it's the same size. Yeah. All right, so our symbol for similar is one squiggle. And we read it is similar to. And we'll get more technical about what we mean by same size, not necessarily same shape, as we go on. So today we're going to talk about polygons. Polygons are similar if corresponding angles are congruent. Now before we finish the rest of this, so our angles are the same. What do we mean by corresponding? We talked about corresponding when we talked about congruent triangles. We matched up the corresponding angles. That was complementary. Mm-hmm. Right. So we match up the small one with the small one, the medium one with the medium one, the big one with the big one, etc. So corresponding means they're in the same place on each shape. So the big one matched with the big one, medium with the medium, small with the small, etc. So the corresponding angles are congruent and the corresponding sides are proportional. So there's why we were talking about proportions, because when we have similar shapes, our corresponding sides are proportional. The angles are the same, the sides are proportional. So let's draw a picture of what we're talking about. And I'm going to call this A, B, C, D, and E, F, G, H. So if A, B, C, D is similar to E, F, G, H, that tells us that the corresponding angles are congruent. So angle A would be congruent to angle E. Angle B would be congruent to angle F. Angle G would be congruent to angle C. And angle D would be congruent to angle H. So the angles would be congruent, the corresponding angles would be congruent, and the corresponding sides, what side would correspond with side AB? EF, right? Those would be proportional, so we could make a ratio of them. That's going to be the same as the ratio between any other pair of corresponding sides. So BC is going to correspond to FG. And that ratio is going to be the same as CD divided by GH. And that's going to be the same as AD over EH. And remember, these are side lengths. So if we make a ratio of any of the corresponding sides, they're going to be the same between the similar figures. And we call any of those, whatever that ratio turns out to be, is the scale factor. So if the scale factor is 1 to 2, that tells us the second one is twice as big as the first one. If the scale factor is 3 to 4, it tells us that the second one is 3/4 the size of the first one. So we call that the scale factor. So these proportions, ratios and proportions, that's the key to Chapter 7. What I always tell the students in Chapter 7 is, if you're trying to solve a problem, when in doubt, write a proportion. Most of the problems in Chapter 7 are going to involve a proportion. All right, question is what we mean by similar polygons. Okay, I just want to look at a few examples now. So triangle ABC is similar to triangle DEF. Which angles are congruent? So angle A, what angle is going to be congruent to angle A? Angle D, right, we just match them up in the same place. Angle B, going to be congruent to angle E. And finally angle C, congruent to angle F. How about proportional sides? Uh-huh. Not congruent, but proportional. So we write a ratio of AB to DE. So we're comparing them using a fraction. And that's going to be the same as, what other sides are proportional? Same proportion, same ratio. BC and EF. So we're just matching those two sides that connect those two to those two. And we get one more. AC to DF. Good. And any of these ratios would give us the scale factor. All the sides are in the same ratio. All right, questions there? All right, here we're going to look at two triangles. Triangles are polygons, right? I want to know, are they similar? So our first question is, are all the corresponding angles congruent? So if we have two angles in two triangles that are congruent, don't the third angles have to be congruent?
Yeah.
Right? Because they have to add up to 180. So the angles, we'll say angles are congruent, so we're good there. Are the sides proportional? We need to check the sides. So we need to see if they all have the same ratio. So what side are we going to compare with the 16 side? 8, the smallest side, right? 16 divided by 8 is 2. What side are we going to compare with the 30? The 15, because it's the medium side. That equals 2. And then finally, 34 to 17 is 2. All the same ratios? So yes, similar. Are we good there? All right, let's look at a couple more shapes. This time we'll look at rectangles. Let me change this around. All right, are these similar? Are all the corresponding angles congruent? Yep, so the angles are okay. They're all 90 degrees. Now we need to say, are the sides proportional? So let's make a ratio of the sides and see if they're the same. What side are we going to compare to the side 16?
The 10 side.
The 10 side, and what do we get when we reduce that? 8 over 5. And then we're going to do the 6 over 4, which is 3/2. Are those the same? So those aren't the same, so they are not similar. They would have to be the same in order to be similar. All right, so now we know how to compare two shapes to decide if they're similar. Let's look at how we actually, the kinds of problems that we're going to be working with a little more in this chapter. So we're going to start with two similar shapes and find a missing piece. So we know that WXYZ is similar to RSTZ. So the big shape is similar to the smaller shape, and the problem asks us to find X. What can we do here? Make a ratio between the corresponding sides. Porter says let's make a ratio between the sides that match up. So we're going to say 24 over 16. And why did you pick 24 and 16? Those are the sides. This says side WX corresponds to RS. And that's going to be the same as the ratio between what other two sides? And which one do I put on top? 20? Because I put the side from the big shape on top here. 20 over X. We know how to solve this, don't we? Cross multiply 24X. 16 times 20, I forgot my X here, equals 320. Divide by 24. And this turns out to be 13.33. Repeating, but this is going to be our main technique for solving problems in Chapter 7. Write a proportion to figure out your problem. The problems are going to have to do with similar sides or similar polygons. Write a proportion. All right, questions? Yes. So this tells us they're similar, and this says that segment WX is corresponding to segment RS. So if we make a ratio between the corresponding sides, it has to be the same as the ratio between any other pair of corresponding sides. And it says that ST matches up with XY, so that's why we picked them that way. Does that make sense? Okay. All right. Good question. Homework. This page 439 are all quadratic equations. So just some practice with those.